It's 1 o'clock, it's time to start. Welcome everybody to the Fields Institute and to the first of the Coxeter lectures, which are part of the thematic program on team geometry, trans series, and applications to analysis and geometry. My name is Yulij Haskell, and I'm the Deputy Director of the Fields Institute. And it's my pleasure to welcome you to the Fields Institute today. You probably know that the Fields Institute for Research in the Mathematical Sciences is located in Toronto, Canada, even though most of you are not actually here in person. The mission of the Fields Institute is to promote fundamental and applied research in the mathematical sciences, understood in the broadest sense. We do this by bringing people together to facilitate the communication and collaboration that sparks new ideas. It may be that you do not know that the Fields Institute itself is on the traditional lands of the Huron-Wendat, the Seneca, and most recently the Mississauga of the Credit River. This meeting place is still home to many people from across Turtle Island, and we acknowledge and express gratitude for the opportunity to live and work on this land. The Fields Institute is funded primarily by the Natural Sciences and Engineering Research Council of Canada and the Ministry of Colleges and Universities of the Province of Ontario, as well as a network of 9 principal sponsoring universities and other sources. It's a great honor to host today's speaker, Yulij Ilyashenko, who will give 3 talks for the Coxeter lecture series. I will now hand you over to Gal Binyamini, who will tell you more about our speaker.
Okay, yeah, thank you very much, Deirdre. So let me say first a few words about Donald Coxeter, after whom these lectures are named. So I don't think I really have to introduce Coxeter for an audience of mathematicians, because he's kind of widely known as maybe the greatest classical geometer of the modern times. But so instead, I'll give a little personal anecdote. So I did my postdoc in U of T about 10 years ago, I guess I started. And I remember when I started, I walked in the building and I noticed a poster commemorating Donald Coxeter. And you know, it had some details about him and his date of birth and death. And I was shocked to learn that he passed away in 2003. So, I mean, I was sure that he lived in the 19th century with, I don't know, Poincaré and Hilbert and these types of people, because his stuff is, you know, it's foundational, it's covered in textbooks. And yeah, so it was I had to write them down. So he's a professor in Russia's High School of Economics, in Moscow State University. He's a professor at Cornell. He's also the president of the Independent University of Moscow. He has led very distinguished careers. Among his many distinctions are 2 invited talks at the ICM. He's also a fellow of the AMS. And I checked today in the Math Genealogy website, and he has currently 35 PhD students who graduated under his advisorship. I mean, maybe more of them are not listed. I don't know. It's hard to keep track of so many PhD students. He also has quite a few mathematical grandchildren already, and myself included. And he's famous for many contributions to dynamical systems, to ODEs, to complex foliations theory. But he's equally famous also for discovering some important gaps in some classical works. And maybe the most notable one is a gap in Dulacs' proof from the 1920s of the finiteness of limit cycles for polynomial vector fields. And this gap that was discovered by Yulij had to do with the inadequacy of regular asymptotic expansions for studying this problem. And actually, having discovered this, Yulij and many others kind of, this was one of the driving forces for them to start to study super exact asymptotics and trans-serial expansions, which is like one of the main subjects of our program. And Yulij will tell us more about this in his 3 talks. So with this, I turn the stage to you, Yulij.
Thank you. Thank you. Thank you both. It's a great pleasure and honor for me to give these lectures. I will outline the theory related to finiteness property of limit cycles for polynomial and analytic vector fields. It has much in common with the trans series. Super exact asymptotic series are one of the most important tools in the study of the monodromy maps of polycycles. Today, I will try to be elementary, probably not very precise, in order to be understandable to a broad audience. The plan of the lecture today is the following. I will say some very few words about Hilbert 16th problem. Then I will speak about non-accumulation theorem for hyperbolic polycycles. Hyperbolic polycycles are separatrix polygons with hyperbolic saddles as vertices only, and the non-accumulation theorem, limit cycles cannot accumulate to hyperbolic polycycles, is rather simple. I will deliver it today. On the other hand, it is a sample for the general theory. To develop the general theory, you should know much more about singular points of real planar vector fields. It is a great theory originated by Poincaré, and now the planar theory is sort of completed. I will speak about that. This theory is used for the study of the non-accumulation theorems for limit cycles. Some major heroes of the story are complex saddle nodes and parabolic germs and their so-called normalizing cochains. I will speak about that. And structural theorem concludes the study and the way from differential equations to complex analysis. So briefly speaking, the lecture today will be transition from differential equations to complex analysis in the study of the limit cycles. So I recall what the limit cycle is. Limit cycle is an isolated closed orbit. Poincaré, who discovered the differential equations are subject of geometry as well as subject of analysis, introduced limit cycles and said that limit cycles, like torches, enlighten the understanding of the phase portraits of differential equations. Hilbert, in his famous list, in the problem number 16, asked what may be said about the number and location of limit cycles of a polynomial vector field of degree n in the plane. This problem is one of the most persistent in the famous Hilbert's list, and I will mention two simplifications of this problem. The first one is uniform estimate. Does there exist an upper bound of the number h of n of limit cycles of a polynomial vector field of degree n? Even for n equal 2, the existence of this upper bound, uniform upper bound, is not yet established. A vast program was initiated by Dumortier-Rousserie and Rousseau in '94. It is largely pushed forward, but not complete. Another simplification is a question: is it correct that the number of limit cycles of a polynomial vector field is always finite? And there is a very close statement, so-called non-accumulation theorem, limit cycles of an analytic vector field cannot accumulate to a polycycle of this field. A polycycle is a separatrix polygon. Its vertices are singular points. Its edges are orbits, heteroclinic or homoclinic orbits that come from one vertex to another one, probably to the same one. And this picture shows the situation which is possible in the infinitely smooth case and impossible in the analytic one. The picture symbolizes a sequence of limit cycles that do accumulate to a polycycle. It's easy to prove that the non-accumulation theorem is equivalent to the positive answer to the finiteness question. Indeed, if we suppose that an infinite number of limit cycles is located in the real plane, and for polynomial vector fields, it's possible to compactify the phase space to extend the field of directions to the projective plane, and therefore the phase space will be compact. If we have a countable number of limit cycles, they have to accumulate to something, and this something cannot be anything else except for a polycycle. I stress that a singular point, an isolated singular point, is a particular case of a polycycle, one vertex and no edges. So, if we suppose that limit cycles accumulate to a polycycle, then an analog of the Poincaré map may be defined for this polycycle. The orbit comes starts on a cross section, makes a circuit near a polycycle, and turns back to this cross section. The first return map is the monodromy map of the polycycle. This monodromy map may be decomposed into a composition of so-called Dulacs or correspondence maps. This is a map of one cross-section to another near a singular point. More precisely, we take an orbit that enters the singular point and a cross-section to it, the orbit that exits the singular point and the cross-section to it, and we consider the map along the orbits of the first cross-section to a second one. And this is the correspondence map, and the monodromy map is a composition of several correspondence maps, a finite number of correspondence maps. This picture symbolizes this composition. Now, let us pass to what Dulac has done at the beginning of 20th. He described the monodromy maps of all polycycles of polynomial and analytic vector fields. For sure, this description cannot be complete in principle. You cannot say everything about these maps. He said something highly non-trivial, and I begin to prepare the necessary notions to state his theorem. A Dulac series is a formal series which is in fact similar to a Taylor series. It is written here. The leading term is just a power term, and the other terms are power terms with the coefficients, but the coefficients are not the numbers, yet they are the polynomials in logarithm. Dulacs series are similar to Taylor series. For instance, if you suppose that a Dulacs series is convergent and consider another Dulacs series which converges to the same function, then the two series do coincide term-wise. This is as easy to prove as the same statement for the Taylor series. So Dulacs series may be considered as generalized Taylor series. And a germ of a mapping of a semi-interval at 0 is said to be semiregular if it can be expanded in an asymptotic Dulacs series. This means that for any n, there exists a partial sum of the Dulacs series such that the difference between the function and this partial sum decreases faster at 0 than x to the power n. So this is the definition of semiregular series. And here are some examples. First of all, any infinitely smooth diffeomorphism at 0 is semiregular. Instead of Dulacs series, it admits an asymptotic, not necessarily convergent, Taylor series. A different example is a power monomial. Any power monomial is a semiregular map. It is just the first term of the Dulacs series. The third example is a particular elementary function that will be important in the future investigation. It is easy to see that this fraction has an asymptotic and even convergent Dulacs series in a neighborhood of 0. The fourth example is quite non-trivial. Dulacs maps of the hyperbolic saddles of an analytic vector field are all semiregular. And this is one of the major achievements of the Dulacs work. He made a great contribution to the study of singular points. Another important property of semiregular maps is that they form a group with respect to the composition. A composition of the semiregular maps is semiregular again. Hence, the monodromy map of a hyperbolic polycycle is semiregular. Now, let us switch to the main theorem that Dulacs proved. He considered not only hyperbolic polycycles, but arbitrary polycycles of analytic vector fields. And his main theorem on the subject is that the monodromy map of a polycycle of an analytic vector field is either flat or inverse to flat or semiregular. I recall that a flat map is a map that has all the infinite number of derivatives equal to 0 at 0. For instance, exponential of -1 over x is the major example. So we will see later the origin of the flat maps in the context, but semiregular maps occur not only as monodromy maps of a hyperbolic polycycle, but in a much more general context. Let us turn back to hyperbolic polycycles. on the in the realm of these polycycles, the Dulacs mistake can be clearly seen. Dulac stated the following lemma: a non-identical germ of a semi-regular map cannot have fixed points near zero. And the proof is simple. Let delta of x be this germ. Consider the difference delta of x minus x. If delta of x has fixed points, then this difference has zeros. On the other hand, delta of x may be expanded into an asymptotic Deluxe series. The difference delta of x minus x may have sort of a leading term. The most interesting case is when this leading term is a term of the Deluxe series after the first power term, polynomial of logarithm multiplied by x to the power nu. And all this difference is this term multiplied by 1 plus something that tends to 0. Indeed, all the higher terms in the partial sum are small with respect to this leading term. And the remainder, the difference between the function and the partial sum, is also smaller than this leading term. So this difference has the expression which is written down, and the right-hand side does not oscillate. So this is the argument of Dulac. Unfortunately, this argument fails when delta of x minus x decreases faster than any power, for instance, exponentially. Then the map delta is semi-regular. Its Deluxe series is simply x, but in general, it may be different from x. In what follows, I will explain that this cannot happen for hyperbolic polycycles, but can happen for non-hyperbolic polycycles. Now I formulate the theorem that shows how bad and complicated is may be the monodromy map of a polycycle. Namely, for any n, there is an analytic vector field with a polycycle whose monodromy map differs from identity by a remainder term which decreases as a tower of exponents. Exponent of negative, exponent to the iterational power n. This discrepancy r is this remainder term is not 0, and this formula is written in the logarithmic coordinate. So the behavior of the germ delta in the logarithmic coordinate psi equal negative logarithm x is studied not near 0, but rather near infinity. So, as I said before, a counterexample like this is impossible in the hyperbolic case. And for a while, we will switch to the hyperbolic case. What is the main conclusion of the understanding of the Deluxe work? The conclusion is that arguments in the real domain are insufficient for our goals. And one should pass to the complex domain. I should say that the teacher of one of my teachers, a great mathematician Ivan Petrovsky, had this tool like one of the major tools. He solved several great problems passing to the complex domain. He gave this idea to his student Landis, and Landis gave this idea to me. So it is convenient to consider a logarithmic chart, zeta, which is negative logarithm of z, and the picture below is drawn in this logarithmic chart. I am discussing now the non-accumulation theorem for hyperbolic polycycles. It is written here. Limit cycles of an analytic vector field cannot accumulate to a hyperbolic polycycle of this field. And here, so-called quadratic standard domains are plotted. On the left, we have a right half plane. I did not draw a disk that should be deleted from this half plane, but please imagine it. We have a special map written in the next slide that brings the right half plane to a domain like this. And so-called almost regular germs will be defined, will have their domain in some standard quadratic domain. And they map this domain to its image. So this is a geometry related to the notion below. When we pass to logarithmic coordinates, to the logarithmic chart, then the Deluxe series written before is transformed to an exponential Deluxe series. The power term that was the leading term becomes an affine map. These two terms come from the first power term of the Deluxe series. And with different polynomials, the terms of the Deluxe series come to this form, polynomials of zeta times exponentials of nu j zeta, nu j are negative and tend to negative infinity. Pj are real polynomials, and this arrow means the monotonic decrease. A quadratic standard domain plotted above is the image of the right half plane with the disk deleted under a map like this. So this is a map identity plus something that slowly, sorry, I made a mistake in this formula. I am sorry. I should write bracket 1 plus this term bracket, or in other terms, zeta plus c multiplied by this square root. So this term tends to infinity, not to 0, but it is incomparable with zeta. Now I can define an almost regular mapping, which is a particular case of a semi-regular mapping. If we write a semi-regular mapping in the logarithmic chart on the real axis, on the positive semi-axis near 0, and it comes to positive semi-axis near infinity under the transition to logarithmic chart. So a semiregular map in the logarithmic chart is decomposed in the exponential Dulacs series. So an almost regular mapping is a holomorphic mapping, which is semi-regular on the real axis, but it may be extended to some quadratic standard domain omega in the complex plane, and can be expanded in this domain to an asymptotic real Dulac exponential series. Expandability means that for any constant nu, there exists a partial sum approximating the mapping with the accuracy smaller than exponential negative u psi in this domain omega. And the analog of the Deluxe theorem about correspondence mappings of analytic hyperbolic saddles. This complex analog says that the Dulac mappings of hyperbolic saddles are not only semi-regular, but they are almost regular. Better to say, these maps written in a logarithmic chart extend to an almost regular mapping in some quadratic domain. Analogously to semi-regular maps, almost regular germs at infinity form a group with the operation a composition. Now, there is a drastic difference between semi-regular maps and almost regular maps. Semi-regular maps are not uniquely determined by their Dulacs series. You may have a semi-regular map which is identity plus something exponentially decreasing. The Dulacs series of this semi-regular map is identity. But for almost regular maps, this is impossible because of an analog of the fragment-Deluxe theorem for almost regular maps. First of all, fragment-Deluxe theorem for functions, holomorphic functions defined in the right half plane. If a function g is holomorphic and bounded in the right half plane and decreases on the real axis more rapidly than any exponential, then this function is identically zero. And the same holds for almost regular mappings, which are defined not in the real half plane, but rather in the quadratic standard domain. The difference between these two statements is very small. Now we conclude that an almost regular mapping is uniquely determined by its asymptotic series. In particular, an almost regular mapping with asymptotic series zeta is the identity. This implies finiteness theorem for the hyperbolic polycycles. Indeed, the monodromy map of a hyperbolic polycycle of an analytic vector field is almost regular because it is a composition of almost regular maps. By the fragment-Deluxe theorem, if its Dulacs series is identity, then the map itself is identity. But if the Dulacs series is not identity, then the map has no fixed points near zero or near infinity in the logarithmic chart, exactly by the Dulacs lemma. When the Dulacs theory is not identity, we can write the leading term of the Dulacs series as it was in the argument of the Dulacs lemma. So here I can put one period. I explained how to prove the non-accumulation theorem for hyperbolic polycycles. Unfortunately, when more complicated singular points enter the game, the situation becomes much more difficult. First of all, I make a conclusion from the previous discussion. The way of proving non-accumulation theorem for hyperbolic polycycles shows that in a more complicated situation, the monodromy map of a polycycle should be extended to a complex domain, and sort of fragment-Mendeleev theorem should be proved for it. On the other hand, this map should be decomposed into some kind of asymptotic series whose terms do not oscillate. This is a very robust scheme of the general investigation. So the whole investigation that I will describe in these lectures and in the mini workshop May 31 will follow this global direction. Now I come back to the Deluxe idea and to my student disappointment when I looked superficially at his memoir. His idea was to study the correspondence maps of singular points and their compositions. But singular points may be arbitrary. They may be arbitrarily complicated. For instance, here I have plotted a face portrait near a degenerate singular point, and such face portraits may be much more complicated. We want to study the correspondence maps for a hyperbolic polycycle along the orbits passing near this point from one cross-section to another. This is Deluxe map of a hyperbolic sector of a complex singular point. But as this point is arbitrary, the first impression is that the plan is crazy. The situation is saved by the fact that the theory of singular points of vector fields in the plane is very strongly developed. And I will say some very few words about this great theory. First of all, singular points in the plane may be of two kinds, monodromic and characteristic singular points. Monodromic singular points are those that admit a monodromy map, a first return map from a cross-section to itself along the orbits. Characteristic singular points are those that have an orbit entering the point with a certain tangency, under a certain direction. A rather simple theorem claims that all singular points of analytic vector fields are either characteristic or monodromic. A little bit more complicated statement is that the distinguishing between characteristic and monodromic singular points is an algebraically solvable problem in sense of Arnold and Tom. Roughly speaking, the problem may be solved by algebraic operations over the Taylor coefficients of the vector fields. The theory of characteristic singular points is very well developed. I will say a few words about that. The theory of monodromic singular point for a long time stayed mysterious. study of monodromic singular points is usually called center focus problem. A better name is distinguishing Lyapunov stable and Lyapunov unstable plots. This problem of distinguishing was completely solved recently by my late student, Natalia Medvedeva. Let us pass back to characteristic singular points because only such points are met as vertices of polycycles. A desingularization theorem due to Bendixson, Lefschetz, Zeidenberg, Dumortier, and others was proved in several steps during the first 2/3 of the 20th century, or probably more. In order to state it, I did a definition of an elementary singular point. An elementary singular point of a planar vector field is a point with at least one non-zero eigenvalue. Classification of such points for smooth vector fields is classical saddles, plots, centers, bilinear terms, nodes, and other class of points, saddle nodes, points that have one zero eigenvalue. I will speak about them more. And the desingularization theorem says that an isolated singular point of an analytic vector field may be split to a finite number of elementary singular points by a finite number of blow-ups. It is not needed to explain what it is blow up. One may think about transition to polar coordinates. The same statement holds for C-infinite vector fields with the Lyasevich condition. Vector fields do not decrease faster than some power near zero. We need a corollary of this theorem, which I will state without explanation what blowing up is. In the picture, we see a correspondence map of a hyperbolic sector of a very complicated singular point, and the corollary of the desingularization theorem claims that this mapping equals to a composition of Dulacs mappings of elementary singular points only. So these vertices are hyperbolic saddles or saddle nodes only. Now let us pass to the study of saddle nodes. First of all, plotted is a face portrait of a real saddle node. A simplest example is x dot equals x squared, y dot equals negative y. You easily see that this system has the face portrait plotted above. And there are two invariant manifolds. A stable manifold consisting of orbits that exponentially tend to zero, and a central manifold tangent to the eigenvector with zero eigenvalue. So this center manifold is much more complicated object, and we study the correspondence map in direction to the center manifold, from the cross section to the stable manifold to the cross section to the center manifold. And the Dulacs map to the center manifold is smooth equivalent to a standard map. So by a smooth coordinate change on the cross sections, we can achieve a standard Dulacs map which is exponential, you may think of -1 over x or over z. But in fact, the situation is a little bit more complicated. The denominator here is not only z, it may be k to z power k divided by this expression. It is very easy to see that this map is semi-regular. Just using the Taylor formula for this fraction. Now, what about the exponential map? We have the factor exponential of -1 over x, and this factor gives rise to exponentially decreasing discrepancies in the monodromy map of the non-hyperbolic polycycles. So the theorem about small discrepancies plays with the saddle nodes. It isn't sufficient to study real saddle nodes only. We should study complex saddle nodes as well. And complex saddle nodes, here is the complex stable manifold. The central manifold is not usually holomorphic. It is just a real arc. Here is a complex cross section, a disk on the transversal line. Here is another complex cross section. And as we have a stable manifold, a disk with a singular point punctured, a monodromy map corresponding to a circuit around this deleted point occurs. This is a curve on the fiber and its first return map to this cross section. And the monodromy map is a parabolic germ. This is a germ at a singular, at a fixed point with the derivative equal to 1. And these parabolic germs enter the game and make a lot of complexities. At this point, I want to ask, Gal, you are the chairman. How much time have I left? We started a little bit later than 8. So
yeah, so I think we started 5 minutes, so maybe around 15 minutes.
Oh, wonderful. Good, good, good.
Is that
Okay,
good?
that's fine. Yes, yes.
Good.
So parabolic germs entered the game, and I switch to this quite different matter. You can forget everything before and just consider germs of holomorphic maps at a 0 fixed point with the derivative equal to 1. And you may ask, what is the analytic classification? What are the normal forms for such germs? The easiest answer is, what are the formal normal forms for such germs? If I cheat a little, then formal normal forms are germs that are equivalent to a shift by 1. For instance, a germ Z divided by 1 minus z is transformed to the shift t goes to t plus 1 by a mapping t equals to negative 1 over z. So in general, there is no mapping that conjugates the parabolic germ in the full neighborhood of the singular point to a time one shift. But the punctured disk, the punctured neighborhood of 0, may be covered by two sectors that are shown here, one on the right, another on the left. And in each sector, there exists a map similar to negative 1 over z that brings this sector to a neighborhood, to an incomplete neighborhood of infinity in the t-plane. And this map conjugates our map with the time one shift. This formula called Abel equation holds. The dramatic question is, do these two conjugacy maps coincide on the intersection of their domains? The answer is they do not at all. And the set of possible transition maps, this is a typo, this is phi, not psi. This composition commutes with the shift by 1. If we go back from here and then go forth using this map, then we bring 2 points that differ by 1 to 2 points source and target of the map F. They again come to 2 points that differ by 1, and therefore the transition map commutes with the time, with the shift by 1. The transition map commutes with the shift by 1. Its difference with identity is 1 periodic and thus decreases exponentially at infinity. This transition map is the famous Ekal-Voronin modulus. And what is most important for us, that the tuple of functions, phi plus and phi minus, forms a so-called normalizing cochain, F normalizing for F. And the transition function is the co-boundary of this cochain. And the co-boundary of this cochain decreases exponentially. So this consideration of parabolic germs introduced one of the major objects of the future study, so-called functional cochains. I will speak more about them in the following lectures, but now I will discuss the Dulac map for the real saddle node to the central manifold extended to the complex domain. This map delta has the form. I read it from the right to left. First goes a normalizing cochain for the monodromy map. Next goes delta standard that was written for the normalized real case. Next goes a holomorphic germ G at a fixed point 0, and this G has a positive derivative at 0. And the map in the reverse direction from the central manifold to the cross section to the stable manifold are called from, and they are just two inverse. Now I come to the conclusion of the lecture today. The monodromy map of a polycycle of an analytic vector field is a composition of the maps to, from, for real saddle nodes, and of almost regular germs that are real on the real axis. So we came to a problem to study the composition of maps very explicitly described. And this is the contents of the future lectures. Thank you very much.
Okay, so let us thank the speaker.
Thank you.